part of the first series about derivatives, and we're going to jump right into exercise series 4. And for this, we're going to solve exercise C first and foremost. So where we're interested in our function f of x is equal to log base 10 of x. Of course, log base 10 of x, you can always just rewrite it as log of x. These things are the same thing, but it's just to make clear that it's on a different base. And we're going to use a couple of things here. Well, one of the things that I recommend you to learn is the basic derivative of the natural log, or ln of x, and the derivative of that is equal to 1 over x. So we can use this to derive this by using one other identity, where you can say, well, the log base 10 of x is the same as writing ln x over ln 10. Okay, so in this case, well, we have, let's rewrite it a little bit, and we get our function is the same as saying ln x over ln 10. And why is this very convenient? Because, well, we can now move ln 10 to the front, because ln 10, as I hope you all know by now, is just a number, and you can rewrite it as ln 10 times ln of x. And now we're interested in taking the derivative of that. Let's open the brackets, say derivative, equal sign, let's move that. So that's equal to, well, some kind of constant. It's not gonna change, it's just gonna remain that constant, times the derivative of ln of x, which is 1 over x. Of course, you could have just learned the basic derivative and you would have gotten exactly the same thing, but here really, if you're a bit clever about rewriting things, you have to know a lot less basic derivatives. Well, you kind of end up knowing them anyways, you just have to know, well, where do they come from? Okay, so that for C. And then let's have a look at D. And here I'm going to show you another trick. And again, you can just learn the basic derivative, especially for a question as simple as this one. But later on, when we're dealing with exponential functions, this trick is going to come in real handy. So let's rewrite this thing a little bit. So we're just going to say it's the same as saying y is equal to 10x, right? Okay, and what's annoying here is that we're dealing with an exponential function. An exponential function, well, it's many product rules, right? It's 10 times itself, and that x times, and that gets really, really confusing. But a very neat thing is that we know that the derivative of ln x is 1 over x. So maybe what we can do is transform both sides. So we can say ln y is equal to x times ln 10, where I dropped that x, right? Because actually what I did is there was x over here, but then remember the logarithm of something raised to a power means that you can bring out that power and you get x times ln 10. And now we're going to take the derivative of this. But remember, we're actually interested in the derivative of y, right? In dy over dx. We're not interested in the derivative of ln y. Okay, but let's do that, and just trust me that we're going to end up somewhere. So basically what you do is you say, okay, we'll take the derivative of this side to 2x, and we take the derivative of this side to 2x. Okay, so let's rewrite it. So we get the derivative of ln y 2x is equal to, and here this we can immediately derive, and we can say this is equal to 1 times some kind of constant, ln 10. Okay. So here, going back to the previous video, well, we can cheat a bit, right? We can use our chain rule, and we can say, well, this, I don't really know, but I do know I can derive that to y, and then we still have to bring in dy dx. And this is very, very convenient because this is actually what we were looking for, right? This was our original equation we were looking for. So in this case, well, you can say the derivative of ln y, following the rule over here, because y is just another type of variable, you could say, well, this is equal to 1 over y times dy dx is equal to ln 10, right? Okay, that being said, we can move y to the other side, and we get dy over dx is equal to ln 10 times y. And this would be a problem if we didn't know what y was. But then here I want to draw your attention to over here We do know what y is. Well, we know that y is 10x, right? So we're going to say this y, we can change it, and we can say this is the same as writing ln 10 times 10 to the power of x. So that's a way to deal with these exponential functions that I strongly recommend, because here it's very easy and straightforward, but we're going to see some examples where it's not that straightforward and you actually have to think a bit more, and then you're going to be very happy that you're able to do this. Okay, then let's move on to the next one, and here we're already going to be very happy that we can use the previous trick. We'll move on to question n, and here it's y is equal to x to the power of 4 plus 5 to the power of x. Okay, let's use the same trick as before, and we can say, well, we can rewrite it a bit as ln y is equal to x times ln x to the power of 4 plus 5. Okay, let's now take the derivative of both sides. And here you will see on the left-hand side, we're always going to end up with the same thing. So see how we did it before? Let's write it out in full one more time. So dl dy derived to x. Then we say, well, we're not really interested. Well, we can't really do this, but we can cheat a little bit. We'll bring in y here, so we still have to bring y over there. So we use our chain rule. And then we just take the derivative of the other side. And here we can rewrite it a little bit, and we say, okay, derive x first, because this is a product of two functions. So remember, a function u times v, if we derive that, well, the rule in general is the derivative of u times v plus u times the derivative of v. So let's do that once. So we derive x first, because that's our u, and this entire thing is going to be v. So we get 1 times, and then we just copy v, and we say, okay, ln, okay, let me write it a little bit closer to one another, x to the power of 4 plus 5. And then we say plus, and now we just write u, x times the derivative of ln x to the power of 4, 5. Okay, in the future I'm probably just going to do this in one go, but let's now have a look at this. And we are interested in the derivative of ln x to the power of 4 plus 5, and we're going to derive that to x. So let's write that out once, and we get the derivative of this thing derived to x, but, well, that's not a basic integral, we don't know that, but we can cheat a bit, and we can say, okay, imagine that that's our variable, so what we are actually doing, so let me give the different kind of notation too, where we say u is equal to x to the power of 4 plus 5. Either one is fine, and as long as it makes sense for you, of u, we're going to derive that to u, and then we have to derive our substitution to x as well. So if we write it out over here, we get the x to the power of 4 plus 5 derived to x. In either way, if we want to do this, well, we get 1 over x to the power of 4 plus 5 times 4x to the power of 3. And then here we can do the same. We get 1 over u times the derivative of u. So we get 4 times x to the power of 3. Let's not forget to substitute u back in, and we get x to the power of 4 plus 5. Okay, so those are two ways of doing it. So we can fill that in over here. So we get ln x to the power of 4 plus 5 plus x times, and now the derivative we found, well, it was over here. We found it was equal to 1 over x to the power of 4 plus 5 times 4x to the power of 3. Okay, let me rewrite it a little bit to make it a little bit more concise, my writing. X to the power of 4 plus 5 plus 4x to the power of 4, x over 4 plus 5. Okay, let's rewrite what we have here on the left-hand side. Well, the derivative of ln y, where y is a variable to y, we just end up with 1 over y, and here we end up with dy dx, which was our original question. We're going to multiply times y on both sides, so this guy is going to disappear, and we're going to end up with this entire thing times y. And then you say, well, this is equal to ln x to the power of 4 plus 5. Let's start our big brackets over here, close the brackets, 4x to the power of 4, x to the power of 4 plus 5 times y, and then we look all the way at the beginning and we find that y is equal to x to the power of 4 plus 5 to the power of x. Of course, if you say, yeah, but I always did it with the rules I was taught in high school, you can definitely use them. I'm not going to subtract points, but in general, I know that when you just learn the rules by heart and these kind of things become more complicated, or I put a different kind of function here, because what I could always do is just do x squared plus 1, people start making mistakes. So in this case, I strongly suggest that you use this, well, basically technique for solving exponential, well, deriving exponential functions. It will always work. And basically, instead of having an exponent that you need to do, you're just dealing with a product rule. So in that case, well, you don't really have to know the derivative of exponents anymore. You can just only know product rules, and then you just have to be here, know the ln one. Okay. Then we get to question O. And this is the one before last one we're going to make together here in the videos. It's x plus 1 and x minus 1 and all of that squared. Okay, in that case, well, we're going to use a couple of rules. Well, the first one we're going to use u over v, and if we derive that, we're going to end up with the derivative of u times v minus u times the derivative of v over v squared. Here, be very, very, very careful. It's negative sign over here. It's negative. And here, we start with taking derivative to u, and in the second part, you take the derivative to v. I see mistakes of this every year on the exam, so really be careful. Okay, so in this case, well, we're interested in the derivative of that, and let's write that out once. So we say x plus 1 over x minus 1 squared, and we will derive it to dx. And then you say, well, but this is not a basic derivative we know, so again, we can use this same rule to cheat a bit, right? So in this case, we're going to say u is equal to x plus 1 over x minus 1. So removing all of this, simplifying this a little bit, we get u squared. We have to derive that to u, and then we still have to derive u to x. Okay, so in this case, well, what do we get? Well, if we take the derivative of that, we get 2, so sorry, the 2 should be over here, u squared. We get 2 times u times the derivative of u over x. Okay, and then we get du over dx. Let's write that out once. So that means that we get 2 times x plus 1, x minus 1, and then times the derivative of this. And let's do that somewhere else. Let's do that a little bit further. Let's take the derivative of u over here. Du dx, x plus 1, x minus 1. Okay, let's uncover u and v. So the numerator is u, and we'll call our denominator v. Okay, then we follow the rule of above, and we say, okay, the derivative of u, x plus 1, the derivative of x plus 1, okay, let me write it out once in full. X plus 1 derived times x minus 1 minus x plus 1 times x minus 1, take the derivative of that, and all of that over x minus 1 squared. Okay, let's rewrite it a little bit. Here, the derivative of x plus 1, well, that's just 1, and 1 times x minus 1 just ends up being x minus 1. So this is 1. This is also 1. So minus x plus 1 over x minus 1 squared. Okay, let's simplify this a little bit. So let's cancel out the brackets. Minus x minus 1 over x minus 1 squared. Or in other words, the x's neatly cancel each other out. We just end up with minus 2 over x minus 1 squared. Bringing that back, filling it in, because this is actually just a part of the exercise, so we get negative 2 over x minus 1 squared. And of course, you don't always have to do this at a different part. It's just here for clarity. I'm doing it here, so basically we're calculating just a little part of the exercise, but if you want to do it in one go, that's totally fine for me as well. So really always be careful with this chain rule, right? And it's always possible to nest even more chain rules, right? Because what I could do here, well, you have two functions, but for example, what I could do is I could first write sinus x plus 1 over here, and then, well, you have a function within a function of a function. So there are many ways of doing additional chain rules, but we're going to have a look at those in the next exercise session, where we're going to have a look at more challenging derivatives. Okay, then let's try the last one together, and here we'll have a look at R. And it is y is equal to 2 to the power of x times x squared. Okay, so the first thing we're going to use, well, it is a function times another function, and if we derive that, we get the following. I'm sorry if I'm boring you with rewriting it, but like this, I really want to drill it in your head. Okay, so we can already write this out a little bit. We can say, well, we're interested in the derivative of this. Well, that's equal to, first, the derivative of 2 to the power of x times x squared plus 2 to the power of x times x squared derived. Okay, let's start with the easy part first. So let's leave this for now for what it is. Times x squared, and of course this is a basic derivative, so you could just do it like that, but to really show you how the previous technique works, I'm going to do it with the previous technique, plus 2 to the power of x times the derivative of this thing, which is 2x. Okay, so we're also using this rule, so x to the power of m derived is equal to, sorry, not, it is m times x, m minus 1. Okay. Now we're still interested in the derivative of 2x. Well, and if you remember all the way from the beginning of the video where we had solved d, it shouldn't be that challenging, but let's work it out once. So we get some kind of other function, and we'll call it z is equal to 2x, and now let's derive that. We'll put ln on both sides, so ln z is equal to x times ln 2. Take the derivative of both sides, so the derivative of ln z 2x, and then here let's derive this side too, so we end up with 1 times ln 2, because this is just a number, or just ln 2. This, you tell me, well, we can't really do that, so we say, well, we can derive it to z, and then we can't forget to derive z to x as well. And that's actually what we were interested in the beginning, because we wanted to know the derivative of 2x. So we find that this is 1 over z times dz dx ln 2. Moving z to the other side, we find that the derivative of z to x is equal to ln 2. Okay, let me rewrite it a little bit so it doesn't look like a z. ln 2 times z. Substituting z back in, we find that that's equal to ln 2 times 2x. Filling that back in, we get ln 2 times 2x times x squared for this part. So this becomes entire this, and this is the x squared plus 2x times, so 2 to the power of x times 2x. Let's simplify that just a tad. We can maybe bring out 2x, and we can rewrite it as 2x times ln 2 times x squared plus 2x. And this is as far as you need to go. You can, of course, maybe bring out x as well. Okay, we can still do that. So we get 2 to the power of x times ln 2 times x plus 2. Okay, but this is really up to you. Like if you end here, or even if you end here, that will be totally fine for me. The main goal is that you show me how to take, that you know how to take the derivatives. Okay, I think these are all the basic techniques for, well, basic derivatives that we need to talk about. The other ones are over there. Maybe let's do one. Let's do one more together. We can do I together because we didn't really do geometric functions yet. So x times the cotangents of x, and I'm going to pretend I have no idea what the derivative of cotangents of x is. So let's take the derivative of that. Well, we first need to take the derivative of x just times the cotangents of x plus x times the derivative of cotangents x. Okay, in that case we can already rewrite it a little bit and say that it's 1 times the cotangents of x plus x times something that, well, we don't know. So let's find the derivative of cotangents x. And for that, let's rewrite it a little bit. So we say cotangents x is equal to cosine of x over sinus of x. Okay, great. If you want to now take the derivative, let's write it on both sides. Well, we can use our quotient rule. Remember, quotient rule, u over v, derive the entire part. It's the same as saying derivative of u times v minus u times the derivative of v over v squared. Okay, let's do that once. So cosine is going to be u, sinus is going to be v. Okay, so we get the derivative of cosine first, which is minus sinus of x, times v, which is just sinus of x, then minus, here we just get cosinus of x, times the derivative of sinus of x, which is again cosinus of x. So make clear that we're solving this over, and then what we're going to do is v squared, which is sinus squared of x. Okay, we can rewrite this a bit because basically what's written here is sinus minus sinus squared x minus cosinus squared of x, which we all know is equal to -1 over sinus squared of x. Okay, now we know the derivative of a cotangents. We have done some derivatives on cosinus and sinus. We can bring it back in and we can say x times -1 over sinus squared of x. Okay, and there you can leave it at. So the derivative is equal to that. Okay, this is it for today. I'm gonna recommend some for home for those who say, well, I'm already very familiar with it. I just want to practice a couple of ones of these. So then I would recommend you make exercise K. You should also make exercise U. Then let's have a look. What's another interesting one to make? Question H is also a good idea. Then you make question H as well. For those of you who have never dealt with derivatives, or for you it's really, really shaky, all of this I'm saying, please make them all, because really we're going to need this for pretty much every class for the rest of the semester. So really it's important that you build strong fundamentals now. Okay, see you all next week on Monday, or Yuri will see you on Tuesday. That being said, have a nice weekend and see you next week. Bye-bye.